Okay. Can you see my slides?
Yes.
Yes.
Okay, great. So this is the outline of the lecture today. We're going to start with motivation, then we'll talk about something called convolutions, which is mathematical operation. Then we'll talk about convolutions over volumes, convolutional layers, pooling layers, and then at the end, what is known as convolutional neural networks or CNNs. This is heavily used in computer vision. So if you're dealing with images, this is really the state of the art right now. So basically, we're going to start with the motivation, and that would be computer vision. So consider an image classifier. You want to classify images basically by taking as an input an RGB image of size 1000 by 1000, so 1000 pixels by 1000 pixels. And it's a red, green, black image, yeah? So it has the 3 channels. So for example, something like this, you have these images and you want to output what is the object in the image. This is, I guess, a museum in Sydney. This is a bridge in San Francisco, if I'm not mistaken, and so on, yeah? This is in Berlin, etc. Okay, so I could use a fully connected neural network with 100 hidden units per layer. Because why I'm saying using a neural network? Because convolutional neural networks is just a type of neural network. Okay, so what do I mean by this? I mean the following, right? The input will be the pixels in the images. So each one of these in the input layer represents one image, and these are just the pixels, the 1000 by 1000 pixels. And then I'm doing a fully connected neural network. So every pixel gets into every neuron in a hidden layer as an input in a hidden layer, and you do summation of the weights of these edges times the pixel values or the feature values, and that gives you a signal. You pass it through some nonlinearity, and that gives you the activation of the neuron. And you pass this to the next layer, and so on. So we've seen this when we were talking about fully connected neural networks, the last lecture. Okay, how many parameters would it involve, this neural network? Any thoughts on this? So parameters means what? Weights.
1 million.
So 1 million, okay, so it's more than 1 million. 1 million is what? Is basically the number of the features, right? So if you have 1000 hidden layers here, then every neuron gets 1 million and its own. In fact, it's not even 1 million, it's more than 1 million because you have an RGB image. So you have, right, the pixels are 1 million, but you have them multiplied by 3. You have the red, the green, and the blue. So every one of these gets 3 times 1 million as a signal. Yeah, so you have weights equal to 3 times 1 million. And then how many do you have of these? 1000. So that becomes 1000 times 3 times 1 million, which is 3 billions per hidden layer, right? So really a lot of weights. So you need zillion of training data. You need such a huge training data to be able to train this neural network. Otherwise, you will not be able to train. You will overfit basically to the training set. Now, this is not a typical of a neural network to have 100 hidden units per layer and to have like few layers like this. So maybe 3 hidden layers or something like this. The final output is a softmax, right? Because I'm doing a multi-class classification. So that's why I have fewer neurons here at the output layer, right? Equal to the number of objects that I want to classify the image to. So here it could be that I'm not classifying the images as really that it's a museum in Sydney, etc. But it's more of a museum, a bridge, a tower, and so on. Yeah, so I have a few classes that I want to classify the image into. Okay, but the take-home message of this slide is that really, if you use a fully connected neural network, you have really large number of parameters or weights that you need to figure out. Okay? Good. So let's see what is convolutions first. A convolution is to use an F by F filter. What do I mean by this? So let's assume this is a 3 by 3 filter. So f is a parameter, and you can set it up to, it's an integer, right? So you can set it up to 3, 5, 7, doesn't matter, right? And it's what is a filter? It's just a set of weights. So here I have 3 by 3 filter, so I have 9 weights, W1, W2, W3 until W9. And I'm going to use it on an image. So let's assume my image was a 7 by 7. I can convolute this image with a 3 by 3 filter, which is a set of weight as follows. You take, right, 3 by 3 part of the image. So we have here a 7 by 7 image. You take 3 by 3 part of it, and you convolute it with these weights. So you multiply the value of the pixel or the feature by the corresponding weight, and you sum. So it has W1 times this pixel plus W2 times this pixel plus W3 times this pixel plus W4 times this pixel, and so on. Yeah. So you get a one single number as a result of this convolution of a 7 by 7 image by a 3 by 3. So you get one single value for the convolution of the first part of the image. Then you move the filter over the image. So you go to the next set of pixels, and you get another number, and then you do another convolution using the same set of weights. So the filter is fixed, right? You have the same set of weights over the different parts of the image, and so on. Yeah. So overall, I have done how many convolutions here? 1, 2, 3, 4, 5. Yeah. So if the width is 7, I would have done 5, right, convolution operations using a 3 by 3 filter. So I get 5 different numbers. All right. What about the height? So I can do this now, go to the next, right, set of pixels. So I move the filter to here. I do, right, these guys. So I start from here and I go all the way 3 by 3. So that gives me a new value or a new convolution, and so on. So how many I have? I have 5 by 5 outputs, right? Because I have 5 from here. I've done these 5 different convolutions and I got 5 numbers. And if I do this vertically, I get also 5 outputs. So in total, I get 5 by 5 outputs. So I took the image and as if I shrunk it to a 5 by 5 new image. Yeah, that's what a convolution is. And how does it work? I just multiply the weights by the feature values. Okay? So this is what is known as a convolution operation. Understood? Okay. So
doesn't make us have less weights.
What is that?
But this doesn't make us have less weights. The problem was إنه عندنا too much weights.
Yeah, it does. I disagree with you. It does because you're using the same weights. So you're not having a weight per feature as before in the fully connected neural network. You would have a weight per every pixel. Now you're using the same weights and you're passing over the image, right? And using the same weights over and over and over again. Yeah, so it's the same 9 weights. So you're using 9 weights to, right, convolute this whole image or, right, pass it through a neural network, but using only 9 weights instead of using 49 weights. You see the difference?
Yes. Yes.
Okay, good.
How do we determine the 9 weights اللي بدنا نستعملهم?
Actually, we're gonna do a training, right? We're gonna do back propagation or something like this. We'll see this in a bit. This will become all clear in a bit. Yeah, but the idea is that I'm sharing weights. I'm not using a large number of weights. I'm reducing the number of weights that I use over my input sample. Okay?
Okay.
Good. So for a 7 by 7 image convoluted with a 3 by 3 filter, you have a 5 by 5 output. Each output acts as a neuron. So you can assume that every output acts as a neuron. Why does it act as a neuron? Because if you look at it, right, what is a neuron? A neuron takes a set of features, multiply them by weights, sum, and that gives you a signal. That's exactly what happens here. So you take 9 pixels here, multiply them by these 9 weights and sum, and that gives you an activation value, one single value, which is the effect of activating a neuron. So really, for a 7 by for every output acts as a neuron. So you have how many neurons? A total of 25 neurons, because you have 5 by 5 output. So you have 25 single values that you were going to output, and that represents 25 neurons. And how many weights? 10 weights. Yeah, because you're using the same weights over and over and over. For every neuron that you have out of these 25 neurons, you're using exactly the same 10 weights. Why 10 weights? Anybody can tell me?
Bias W0.
W0, exactly. You have the W1 till W9, and then the W0, the bias. So that becomes 10 weights. Okay. Compared to what? Compared to if I had a fully connected neural network, I would have had 25 times 50 different weights in this case. Why 25 times 50? I'm using 25 neurons, so you could assume that I'm using 25 neurons. Yeah, so every neuron would be, if it's fully connected, then I have the 49 pixels plus the bias, that's 50, connected to this neuron. Yeah, and these have different weights from the next neuron and the next neuron out of the 25 neurons. So I have a total of 25 times 50 different weights in case if I use a fully connected neural network, right? The huge difference in the total number of weights between a fully connected neural network and a convolutional neural network. Okay, so 10 weights versus 25 times 50 different weights. Does this clarify to an extent that you have fewer weights in this case? I assume yes. Okay. Good. So let's see what is these convolutions, right? So the weights, what do they mean? So let's say the weights are set to this. The filter is weights are set to 1, 1, 1, 0, 0, 0, minus 1, minus 1, minus 1. Yeah. So let's just apply the convolution operation and see what do I get. The new image that I get. Okay. So what do I get? I get 3 plus 1 plus 2, because all of these weights are 1. So I get 3 plus 1, that's 4, that's 6. 0, so these go away. And then minus 1, minus 8, that's minus 9, minus 2, that's minus 11. Minus 11 minus 6 is minus 5. So I get here a minus 5. Okay? And then the next one, so it would be over these 9 pixels, apply the filter. Yeah, so I get minus 4. And then I get 0, I get 8, and so on. So I get this output after applying this 3 by 3 filter over this image. Yeah.
Doesn't this have a lot of negatives compared to the first one?
Yes, you can get negative signals, but not necessarily compared to the first one. You get more negatives because remember the weights, right? You learn them. And so the weights could be that some of them are positive, some of them are negative, and you end up with negative values. So it's not necessarily that you would get more negative values here compared to the fully connected neural network. And again, I'm using here a special filter, right? So I'm assuming that the weights are 1, 1, 1, 0, 0, 0, minus 1, minus 1, minus 1, right? Just I want to illustrate something by this. Well, in reality, these weights you'll have to learn them. So they could be any values. Yeah, so they're not going to be. Yeah.
Yes.
All right. So what is, if the weights were set to this, or the filter was set to this, what does it mean to apply it over an image, to apply, these convolution operations over an image using this filter? It basically does the following. It takes this image and makes it look like this. Yeah, so it acts as if it's an edge detector, right? It tries to, forget about the non-important pixels and focuses on the edges only, right? So it's detecting edges in the image. So if you really look at the image that you get out of applying this convolutional operations, or applying this filter on the input image, you get something like this. The image that you would observe, right? Because you get some numbers and you can visualize these, and that's how the image would look like. So it's somehow an abstract visualization of the input that you have. Yeah, if you use the filter like this, of course the filter is going to be some weights, but you will get some rendering of the input image, yeah, based on the values of the weights. Okay. So let's understand why this is an edge detector. If I use these weights, so 1, 1, 1, 0, 0, 0, minus 1, minus 1, minus 1, why does it act as an edge detector? So here's an input image, a very special type of an input image. It's, 10, 10, 10, so very positive. Half of it is very positive, and the other half is 0. Very positive means white, 0 means gray, and very negative means black. Yeah, so basically 1 or multiplications of 1 is white, 0 is gray, and minus 1 is black. Okay, so I take this and I apply this filter to it. What is the filter? It's going to be the 3, so 30, 0, minus 30. So I get a 0 here. And then the next one, it's 30, 0, and 0, so I get a 30, and so on. Yeah, so I can compute the value of every cell here based on computing this image with this filter. Okay. So why does it act like an edge detector? Because you're looking at the following, right? There is a high edge here. It says the following, right? This image, if you look at it abstractly, it's a white region and then followed by a gray region. So there is a sharp edge in the middle. If you apply this filter on it, this is what it gets you. It gets you a gray region, then a white region, because these are like 30, and then you get a gray region. So they managed to do, as if it's zooming in onto this edge, right? It's magnifying the edge shown over here. Okay, just I'm giving you an intuition about what convolutions do. Yeah, they do really edge detection. Of course, in practice, right, these weights are set at random, and so it's not exactly like this. But they tend to act as if they are edge detectors in the edge. Okay. All right. So this is a vertical edge detector. This is a horizontal edge detector. Yeah. So if I apply this one, this filter over this image, I get right that I have 30, and then zeros, and then minus 30s, so I get zeros. And then the next one would be 20, and then zeros, and then minus 20, so I get 0. So the first row becomes all 0. And so, right, eventually, I get, right, this acts as if it's a horizontal edge detector. Yeah, because I get, right, the gray here, the gray here, and then some other, values in between. So here's how it looks like. Let's assume this is the input image. If I apply the vertical filter, the vertical edge detector, this is what it gets me. It gets me, right, detecting these edges. Yeah, so the vertical edges in the images. So the bars here, right, the silhouettes of the people, and so on. And the horizontal one detects, right, the horizontal bar here, and the bicycle, and so on. So each one focuses on certain types of edges. Yeah, this is just an intuition again about what it means to do a convolution operations. Okay, now in reality, we typically do filtering with some stride. So let's see what this means. Again, I'm going to use an input image of 7 by 7 pixels and then 3 by 3 filter, which is defined by 9 different ways. Okay, so the stride means the following. Instead of going shift one step to the right, I'm going to shift 2 steps to the right. So I go from here, I stride off 2. So that's a stride of 2. Okay, and then I do a stride of 2, I get this. So what is the size of the output in this case? If I have a stride of 2, I get an input of 7 by 7, and I do a stride of 2. What is the output?
3 by 3.
3 by 3, exactly. So I get 3.
ليش بنعمل striding؟
نعم.
ليش عم نعمل striding؟
So because you focus on different parts of the image, yeah. So you don't wanna, if you do this, you might get redundant information. So you wanna do this so that you don't get redundant information. Okay.
Okay, so striding basically عملنا 2 pixels.
عملنا 2 pixels بالضبط. All right, so I get 3 by 3 output. Because I'm gonna do a stride at, also vertically. Okay. Another thing that I commonly do is to pad the border with zeros. Why? Right? What do I mean? I pad the border with zeros. I take, this is my original image, and then I add zeros, right? Additional pixels to the border, which have the value of 0. Why do I tend to do this? To overcome output shrinkage after convolution and incorporate more info from the edges. Okay. So what does this mean? Remember, if I don't have the padding of 0 and I'm doing stride of 2 or stride of 1, then I'm gonna move right from here to here. If I'm doing a stride of 1, then to here, then to here. So this part, the edge of the image, is only incorporated once, one single computational operation, right? So it affects the output only once. Whereas, right, this would affect it multiple times, this would affect it multiple times, and so on. So by padding to 0, I managed to take the edge information into consideration multiple times, because now I start from here. And so, right, this edge would appear in multiple computational steps, depending, of course, on the stride. But also it allows you to overcome output shrinkage after computation. So in the previous example, we had the 7 by 7 image. We ended up with an output of 3 by 3, right? With padding of 0, I can get to the same size of the input image. And that helps you to write, because you're going to use this in various layers. And so it's better to have, you don't have like huge shrinkage of the input image. So let's see, what is the output size if your input is 7 by 7? Use a filter of 3 by 3, a stride of 1, and a padding of 1. Just try to count it.
Sir, just let me get this right. Padding means that we don't calculate the padding مع calculations كلهم, أو...
We calculate it as if it was an original pixel, right? But the values are 0. But you have here W1 times 0.
Oh, we added the padding. It's not something. Oh, okay.
We pad the image. So the image is like 7 by 7. I add a padding over all the borders with values of 0. Yeah. So as if it's you're adding a frame to the image. Okay. So what is the output size? Try to move the filter. I have a stride of 1. So it's going to move here next, then here next, then here next.
7 by 7?
It's 7 by 7. Excellent. It's exactly 7 by 7. Yes. Right? Because I have here 1, 2, 3, 4, 5, 6, and 7. I get 7, and then the same thing because it's symmetric over down there. So I have 7 by 7. So it helps really with the shrinkage of the output, and it helps also to incorporate the information from the edge, because I get this, right, this edge once here and then once here, and then so at least twice. I get it twice. Okay, so summary of convolutions. The input is n by n. The filter, which is right, the set of weights that you have, is f by f, so symmetric and typically odd, right? So either 3, 5, or 7. You have a stride, which is a hyperparameter, and you have a padding, which is hyperparameter. So you can set pad to 1, pad to 2, then you would add a border of size 2 with values 0, and so on. Based on this, you get the output size to be n plus 2p minus f over s plus 1, the floor of this. So n plus 2p minus f over s plus 1. Yeah, let's see some exercises on this. So what is the output size if you have an input image of size 7 by 7 and you're using a 3 by 3 filter with a padding of 2 and a stride of 2? So S is the stride.
5 by 5.
Let's calculate it. So I have 7 and 7 plus 4,
Yes.
11 minus 3, that's 8 over 2, that's 8 by 2 is 4, plus 1 is 5. So I get 5 by 5. Okay. What is the input, the output size? If you have an input image of size 7 by 7, and using a 3 by 3 filter with a padding of 0, so you don't do any padding, and a stride of 2.
3 by 3.
So I have 7. Let's calculate it. 7 plus 0, because the padding is 0, minus the filter, which is 3, that's 4, divided by 2, that's 2, plus 1 is 3, you get a 3 by 3. Excellent. What is the output size if you have an input image of size 7 and you're using a 5 by 5 filter with a padding of 2 and a stride of 1?
7 by 7.
Let's see. So I have 7 plus 4, that's 9, right? Because you have a padding of 2, minus the filter, which is 5. So 9 minus 5, that's 4, divided by 1 is 1, plus 1 is 5. So sorry, then I miscalculated. So it's
Yes, it's 13 minus 5, 11 minus 5, not
11 minus 5.
Yeah, 11 minus 5, that's correct, that's 6, over 1, that's 6 as well, plus 1, that's 7 by 6, exactly. Type, how much padding is needed to get an output size of 7 by 7 if you have an input image of 7 by 7 and you're using a 3 by 3 filter with a stride of 1? So what do I need to know? What is the unknown here?
P.
P, exactly. And I have everything else.
It's 2 or 1 point. No, it can't be a decimal, right?
It's 7.
Oh, la, never mind.
The padding 7 is not realistic. Let's calculate it. 7, we have the output is 7. You have n is what? Is 7 plus 2p minus f, which is 3. So n plus 2p minus 3 plus 1. So 7 plus 2p minus 3, that's 4 plus 2p plus 1. That's 5 plus 2p is equal to 7. So you pass the 1 over there, so you get a padding of 1. Exactly. Right? 2p is equal to 2, and you get a padding of 1. Rasha, I didn't get your comment. What do you mean by p?
You were asking
what is the unknown?
You were asking what's the unknown, and she answered.
Yeah, exactly. Yes, you're right. So p is the unknown. So everybody got why p is 1 here?
Yes.
Okay, perfect. All right. Okay. Now we'll talk about convolutions over volumes, because typically the image is a volume, right? It's not a one-dimensional image. Oops. Am I still there? Hello? Hello?